is Francisco Villaescusa-Navarro, but a lot of people call him Paco. He got his PhD from Valencia in Spain, and then he held a postdoc position in Trieste in Italy and at the Flatiron Institute in New York. And now he's an associate research scholar at Princeton. His areas of expertise is studying of the large-scale structure and body simulations with neutrinos. And recently he also got really interested in machine learning. And today he is going to tell us about his work on cosmology in the machine learning era. And before he starts, he said that he will be very happy to be interrupted during the talk. So feel free to unmute yourself if you have a question. And sorry. And yeah, Paco, you can start.
Thank you, Lena. Thank you. So yeah, please, I mean, interrupt me at any time. I really prefer that to be more interactive also. So I'm going to tell you a little bit about what we have been doing, like maybe for the last couple of years, like going deep into the machine learning side and try to apply this to cosmology and also astrophysics. So, let me see. So, I cannot, okay. Yeah, I think. So this is the outline of the talk. So I'm going to very briefly give you just a motivation, basically what is the final goal that we are trying to achieve here. I will spend most of the time in the talk talking about the small scales. So basically, what are the benefits if we go to smaller scales in cosmology, but also what are the problems that we need to address in order to get these benefits. And then I will be claiming, and I know that this might be a little bit controversial, but I will be claiming that machine learning is probably the very best thing that we can ever do. Right now, it's a black box. We don't understand anything, but hopefully, if we keep pushing in this, everything will be more interpretable. And I believe that this is the very best that we can do, I believe. And then finally, just if I have time, I will tell you this vision that we have been working between Princeton and New York with many people. Okay, so motivation. So as all of you know very well, we have this model, the lambda-cold matter model. And just to emphasize, this model is amazing, right? I mean, it's incredibly, sometimes it's astonishing how something that in principle is not so difficult. I mean, I'm able to understand this, so it shouldn't be that difficult. How this simple model is able to really explain such a large variety of cosmological observation. From the temperature of the CMB at redshift 1100 to the spatial distribution of galaxies like at low redshift. Going from the properties of the Lyman alpha forest at redshift 2 to 4, to weak lensing and all this. So I'm leaving aside this H0 tension that who knows? I mean, I'm not entering there. I'm assuming that lambda-cold matter is able to explain everything. So in this model, at the end of the day, what we have is some parameters. We have omega matter, omega baryon, all these parameters. So what I will say is that the goal, the final goal in cosmology will be to constrain the values of these parameters with the highest accuracy. That's, I think, the goal. So why do we want to constrain the value of, I don't know, omega matter or the neutrino masses with the highest accuracy? So the reason behind this is that by doing this, we are hopefully going to learn something about the fundamental physics. So for instance, if we are able to get a very, very small error on the neutrino masses, we are going to be able to put a constraint on the absolute mass of the neutrino masses. That is one of the ingredients of the standard model of fundamental physics, of particle physics that we still don't know. We are going to hopefully be able to say something about the neutrino hierarchy, which is also something extremely important. With a small error on W0 or WA, and depending on the value of this, we might be able to say something about dark energy, but this is also a very, very fundamental question. And things about the initial properties of the initial condition in the universe, and so on and so forth. So we want to constrain the values of the parameters with the highest accuracy. That's really the final goal, I will say. So how do we do this in practice? So what we do is we carry out some observations. So for instance, in this talk, I will be thinking in galaxy redshift surveys. And you can see here one image. So you measure the position of galaxies on the sky on the redshift. And then what you do is to compress all this information into a lower dimensional vector. And typically we are thinking in the power spectrum. We don't know how to work at the field level. I will be talking about this later in the talk. But right now I will say that we don't really know how to work at the field level with this gigantic amount of data. So we need to really compress this into a lower dimensional vector, something that is more tractable. And then from the theory side, what we do is, given some values of the cosmological parameters, we compute what will be the theory prediction for this observable. So let's say the power spectrum. So what will be the amplitude and shade of the power spectrum for this value of the cosmological parameters? And then you do an NCNC, you vary the cosmological parameters, and you try to match like observations with theory. And this is the way that you constrain the values of the cosmological parameters. This is like the standard method. So what I will say is that one of the most important questions here is the following: is what Samara statistics should I compute from this field in order to get the tightest constraint on the cosmological parameters? That is, at the end of the day, what I really care. So this is, I think, a very, very fundamental, a very deep question. So we know the answer of this question for some particular cases. So as all of you know very well, if you have a Gaussian density field, then we know that this field is completely characterized by the power spectrum or the two-point correlation function. You have one of these fields, you compute the power spectrum, and you are guaranteed that you are going to be able to get the tightest constraint on the cosmological parameters ever. You can measure other things like the peak abundance, the voids abundance, any other thing that you can imagine. You will never get tighter constraint on the parameters than this. The question is, what about this monster? Imagine that you have a non-Gaussian density field. So in this case, this is also a very well formulated, mathematical question. And we have been asking this question to mathematicians, is that given this field, how should I compress the data in order to maximize my feature information, in order to get the tightest constraint on the parameters? So the answer to this is that this is mathematically untractable. This is what I've been always told. At some point, I was even looking in Wikipedia, what exactly does it mean? So it's really, really hard. It's basically impossible to do this analytically. That's my understanding. So basically what I will say is that right now, the only thing that we know is that if we measure the power spectrum of this field, this will contain cosmological information. We can put constraint on the cosmological parameters. If we measure the bispectrum of this field, this will also give us information. If we measure the peaks, the abundance of peaks, the distribution of peaks, the same thing for the voids, the underdense regions, all these things contain cosmological information. So right now, the only way that we have to really answer this question, like what semi-statistics is the best one, is to just try one, try another one, compare with another one, and see which one is the best one, unfortunately. So in summary for this motivation part is that the final goal is to constrain the value of the cosmological parameters with the highest accuracy, and that we don't know how to do this for non-Gaussian density fields. So let me explain what has been our approach here. Consider one generic observable, statistics, let's say for instance the power spectrum. And then you have some parameters, the value of the cosmological parameters. There is this framework that all of you are aware, that is the Fisher matrix, that is a very
Did we lose the speaker?
Seems so.
Yes.
Okay.
It's frozen.
I hope it doesn't go too long before realizing.
He's either frozen or he's holding very, very still.
It may be the US has collapsed. They're dealing with a lot right now.
Yeah, well, they've dealt with worse, haven't they? I don't know.
Problem is, depending on how many screens you have in Zoom, you sometimes all your, you don't see, the only way you can tell you're frozen is if everybody else is frozen. But if they're all minimized and you're just looking at your talk, it's not always up.
Yeah. Well, hopefully he's realized that it's disconnected now. So does anybody have a phone number from the speaker?
Yeah, maybe in Zoom or like in Slack or something. I just looked and none of the groups I'm in Slack, Parker seems to be, but I'm sure somebody must have it, right?
Yeah, we'll contact him via the phone now.
Okay.
Okay, so he said that he lost the connection. Hopefully he can connect back in a few minutes.
Okay, thanks. Okay, good, good. You're muted, Parker. You should unmute yourself. There you go. Good.
I apologize. I mean, usually what this happens is that it might be also happening during the talk. So I apologize in advance. Yeah, I mean, hopefully it will not happen again, but sometimes my connection is, yeah, so I'm really sorry. Okay, so yeah. So basically what I was saying is that in principle, we only need to compute this Fisher matrix. So if you want to compute this for any generic statistics, this might be hard because you need to really compute, for instance, how does the statistic look like in the fully nonlinear regime? Or as many of you know, computing the covariance matrix for a generic statistics is something that is not trivial at all. So our approach here has been to do this like fully numerically. And this is what I would like to quickly introduce these Quixote simulations that some of you are, of course, authors of them. So basically the simulation has been designed to really quantify, to do this Fisher matrix calculation for any generic statistics. So what is this suite? So this is a suite of more than 44,000 full embodied simulation. This is the largest set of embodied to date. We have more than 7,000 different cosmologies in the hyperplane of omega matter, omega baryon, and all these main cosmological parameters. Let me see, I don't know if there is a comment or something. Okay, sorry. And we have more than 50 trillions of particles in the universe. So the total volume that we cover in this simulation is larger than the volume of the entire observable universe. So we have really a lot of statistics. We have also identified billions of halos, billions of voids. It took really a very long time to run this, 35 million CPU hours. And we have generated this petabyte of data that this is really what is basically dragging all my energies. I'm always basically fighting with system administrators in Princeton, system administrator everywhere. So yeah, if you have like some hundreds of terabytes that you would like to spare, I'm kidding. So everything is publicly available. You can just go to the web page and you can download the data, or if you for some reason need to access the snapshot and you cannot really move like 1 petabyte, that I know it's not trivial, let me know and I can maybe try to open an account for you in Princeton. Okay, so very quickly, just I would like to give some credit to the people who are involved on this. Of course, you know, here there is Elena and there is Andrei, and there is many people. So this is mostly people from San Francisco, Berkeley, Stanford, a lot of people from Princeton and New York. So this is a kind of joke. I think people in Princeton, they call New York like Princeton North, but people from New York, they call Princeton like New York South. So I always have to be maybe careful. And then a lot of people also from Paris.
You can't deny that Princeton's in New Jersey. Very different.
I know. So, okay, so power spectrum. So let's consider the power spectrum and let's see why this might not be the best statistics. What I'm showing here, this is the error that you get on omega matter as a function of the maximum K, the scale where you cut. So what you can see is that as you go to smaller scales, as you go to higher K, the error decreases, which is expected. So there is more modes and the error decreases. But at some point you can see that the error saturates. And this happens for all the parameters. Beyond, I think like 0.2 or 0.3, there is really not much information, but this on the power spectrum.
Sorry, how are you getting these curves?
So this is basically using this Fisher matrix.
Mm-hmm.
And what I'm doing is I'm using all these Quixote simulations. So basically I compute this term numerically, and we also have like 15,000 simulations. So we compute the covariance fully numerically.
Mm-hmm. Okay, I see.
And just evaluate this fully numerically. Yeah.
Thanks. Mm-hmm.
But at higher K, does that saturation stop? That was my impression.
Yeah, I mean, this simulation, I will not really trust all the way to K of 1 because, you know, they don't have the resolution enough.
Right.
So I can try to push this. I think if I push this a little bit more, I get a little bit tighter constraint, but I don't know if these are some numerical artifacts.
Mm-hmm.
That's why to be conservative, I should stop like at 0.5 or 0.6, 0.7.
Yeah, with your simulations, right? But
with my simulations,
my impression was that the saturation stops if you go to much higher K.
Yeah, but people has also done kind of similar exercise with the full covariance matrix and everything.
Like the physics I thought behind this saturation, you know, just was that, you know, on these Ks, you know, sample variance in like the biggest halos dominates. Right. And right, you know, so therefore then it makes sense that at higher Ks where like those few biggest halos don't dominate, that you therefore then pick up information about the primordial power spectrum again.
Mm-hmm, mm-hmm. Yeah, where you start seeing the one halo term, I guess.
Well, right. So you see the one halo term, you know, but the sample variance from like the top like 2 biggest halos isn't controlling the one halo term, right?
Okay.
That's the problem happening here, I thought, right?
Yeah, we haven't taken a look in detail on this, but one of the things that we have been, that I can claim is that this is also due to parameter degeneracies. Depending on what parameters you use, if you only use sigma 8, you can really get information by going to a small scale. There is no problem. But when you start putting a lot of parameters, there are some degeneracies, and then you don't really gain much information. And then the covariance matrix becomes highly non-diagonal. So you are also losing some information there. Mm-hmm. Yeah, but you are completely right. I mean, I have seen also these works, and yeah. Okay, so basically, the takeaway from this plot, at least if we don't go to the super small scales or a smaller scale that Neil is talking, is that the information saturates, at least to K of 0.5. If we go to much higher K, we would also have to worry about baryonic effects, and I will be talking about this later. So it seems that maybe we need to take a look at something else. So now, because we have basically this tool with simulation, we can basically compute anything that we want. So what I'm showing here is constraints on the value of the cosmological parameters using the power spectrum. This is the matter power spectrum, taking Kmax to be 0.2, something very conservative. And these are the things that you obtain. Take a look at, for instance, neutrino masses. I mean, these are not very good constraints at all. These are too heavy. What happens if you now consider the halo mass function, the abundance of clusters? So what you obtain is these blue contours. And what you can see in many cases, for instance, I don't know if you take a look at this panel, H, you can see that you are not really constraining the parameters much better than the power spectrum, but you're going to break in these degeneracies. When you combine these two guys, you're going to really break these degeneracies. What happens if you use, for instance, the Boyce size function? So this is what we obtain when you use this green line. Again, individually, it's not really competitive for most of the parameters. It seems to be, for instance, competitive with NS. But the good thing is that what happens when you really combine everything? For instance, take a look at this plot, at this panel. This is neutrino masses versus sigma 8. And this looks like a perfect, the perfect way to break the degeneracy, right? I mean, I will not have even imagined doing this in a better way than this. When you combine everything, and when you put the full covariance matrix and everything, you obtain these black contours that are a little bit hard to see. For instance, I don't know if you can take a look at here. You get very tight constraint on the parameters. So for instance, for neutrino masses, we are getting like a 3 or 4 sigma. I will be talking about the work of Elena next, but it's still very competitive. So all my takeaway from this slide is that if you consider things beyond the power spectrum, you are going to break these degeneracies. You are really extracting information from different elements of the cosmic web, and this is going to help you a lot. So this was one example. I'm pretty sure that all of you know the work of Elena Masara for the first time using the MAR power spectrum. That is basically the standard power spectrum, but you put a weight for every particle or for every galaxy. And this was beautifully well, right? I mean, and as you know, Elena, this has raised a lot of attention. I think there are now many people working on this, and of course you are leading the field. But for instance, take a look at this panel. This is neutrino masses. We are claiming a 5 sigma constraint on the neutrino masses using just these very simple statistics. I think Chan was last week there, I think he told me. So I'm pretty sure he has told you everything about the bispectrum. We have also computed the information contained on the full bispectrum. Again, there is much more information in the bispectrum if you go to smaller scales than with respect to the power spectrum. And he has now done everything with the galaxies, and the conclusion is the same. And Cora was a postdoc in Cambridge. He has done the same analysis using the PDF. Another very simple thing to measure, but and conclusion is the same. When you consider when you go to smaller scales and when you take an statistics that is different than the power spectrum, you are going to gain a lot of information. Sometimes you are really taking. You don't agree with that?
Oh, no, sorry. Like my internet, I think, was bad. So I lost you for a bit. Sorry.
Yeah, I think we lost you for a second there, but looks like you're there. So that's good. Mm-hmm.
Yeah, I apologize. I was mentioning that this is for the PDF and that information contained on small scales on things beyond the power spectrum sometimes, and in many cases, is higher than the one on the power spectrum. So this is what I just wanted to emphasize here. And I think this is probably not so new or so surprising. As we go to smaller scales and as we go to things beyond the power spectrum, there is a huge amount of cosmological information there. That's basically the only thing that I want to emphasize here. And I think this is not surprising. Okay, so this is the case. Then let's go to smaller scales. I mean, why not? I mean, let's go to K of 100. I mean, why not? So then there is a problem that we will have to deal with, and it's baryonic effects. So as all of you know very well, there are things like supernova feedback, there are things like AN feedback that we know, and we expect that this will modify the distribution of matter, and it will also change like the properties and the clustering of galaxies on small scales. The problem here is that we don't really fully understand the physics of these astrophysical effects. So what I will be claiming, and again, I don't think this is very surprising, is that the best conservative solution is to marginalize over these guys. Let's marginalize over these guys. But then let's go to K of 100. Let's go all the way there. Okay, so now I have to make a small parenthesis because I'm gonna be talking about the neural nets. So since Elena told me that maybe not everybody is familiar with neural nets, I just wanna give like a very, very small kind of flavor of what exactly is this and how you should think about this if you are not familiar with this. So what is a neural net? So imagine that you have some input and some output, and this could be completely general things. For instance, let's say that you have the temperature today, the humidity, the pressure, the wind pressure, all the properties, climatological properties that you can imagine. And then you want to predict the rain probability. And imagine that there is a function relating the two of them. It won't be very complicated, but imagine that there is some function relating this. Or imagine that you take an image and you say, this is a cat. There is a relation between the two. Or imagine that you go to 3D and you take one of the simulations or the real universe and you say, this is the value of the parameters. If you have an output and you have an input and there is a function relating the two of them, neural nets are basically a mathematical construction that is going to approximate this function. Always. There is a mathematical theorem for this. It's called the universal approximation theorem. And it's telling you that under very general conditions, maybe there is some particular condition where this doesn't fulfill, but for incredibly broad conditions, this will always apply. So this is incredibly powerful. Imagine you have an output, you have an input, you know that they are related, but you don't know how to relate them. A neural net will find this relation for you in such a way that if now you have a new input, you can predict what will be the output of this. Just a little bit more of detail, let me just give you this last slide on how exactly this works. So this is a very simple neural net. This is, I think, called the perceptron. So imagine that you have two input, x0 and x1. So imagine that this is like the temperature and the humidity today in New York. And what you want to predict is if the probability that is going to rain today. So what you do is that these two neurons, you are going to pass here. And what is this H0? So this H0 is nothing like this. You take your input and you make a linear combination. And these are three parameters, W0 and W10 and this bias. And then you apply a function. And this is going to be a non-linear function. But that's all you are doing. And this value that you compute, you store it here. You do the same thing for all the others. So for instance, for H2, you are making a linear combination of the input. These are three parameters again, and then you apply some non-linear function. Once you have this is what we call a layer. You do exactly the same thing here. So for Y, you have these three neurons that are contributing. You make a linear combination of them, and then you apply some non-linear function. You can apply or you cannot in this particular case. But so what are these non-linear functions? These non-linear functions can be as simple as this. Something that if your argument is positive, you leave it, and if the argument is negative, you put to 0. That's something that we use every day. This non-linear function is called the ReLU. And what you can see is that at the end of the day, you are really building you are writing your Y as some function of your input with all these parameters. So at the end of the day, the only thing that we are doing is basically fitting these three parameters in order to match Y given X0 and S1. That's it. That's really everything. And there are, of course, ways to find the best weight for these parameters and everything. So that's basically all I want to say about neural nets. Just think that if you have an input and you have an output, a neural net will basically find the way to match the two of them. Okay, so we were talking about baryonic effects. So I want to show you something that I believe is very beautiful. This is very simple, but in my opinion, it's very beautiful. I want to show you with a toy example where I think at least we can understand everything. That neural nets can extract all the information that you have on the field they're going to be able to extract it. Or in other ways, they're going to find the optimal estimator to extract the information. I will also show you that neural nets can learn to marginalize over baryonic effects automatically. You will see later. And then the third thing is that I want to show you that neural nets can extract cosmological information that might be embedded into the fully dominated astrophysics regime, in the regime dominated by baryonic effects. So let me show you how this works. Let me see. So we are 12. Okay, so I think I should finish, Elena, by 12:20 or?
Yes, or 25. Just give 5-10 minutes for.
Sure. Okay, so what I'm considering in this example is 2D Gaussian density fields, and you can see here in this panel. These Gaussian density fields are constructed with a very simple power spectrum. It's this. This is the power spectrum. I have some amplitude A, and then I put like the power of. I basically divide by the square root of K, just to take some power law. So what I want to do here is that I want to take one of these maps, and I want to basically constrain the value of A just with a map. So what I know is that if I'm doing this in being myself, I will need to compute the power spectrum of this map. Then I will need to write down the likelihood, and then I will need to maximize the likelihood. And this is the way that I will get the value of A. Now what I want to do is that I want this to be done by a neural network. Basically, my input is going to be this map, and my output is going to be this A. And you can think of this like the cosmological parameters. So basically, I want to train a network to predict the value of A. So yeah, very simple is that you input the map to the neural net, and again, you feed all these weights, and you can have millions of these weights. Millions is actually something like a very small network. I think people these days are even working with tens of billions, I believe. But yeah, think that 1 million free parameters is something small. And then you predict the value of A. All right, so I train this network, and when this network is working, what I do is the following. I create 100,000 maps with a fixed value of this parameter. Let's say A equal to 1. And then the network, every time that you put a map, the network is going to give you a value of A. It can be 1, it can be 0.97, it can be 1.3, whatever. What I'm showing here, this is the distribution of the values of A that the neural net is predicting. This is the distribution. And you can compute the mean, it's given by this, and you can compute the error, the standard deviation. Okay, so very nice. But now what I can do is that, because this model is so simple, I also know what is the best, I know what is the tightest error that I can get on the value of A. Because I can just do a very simple Fisher matrix. I have my power spectrum, so I can just do a Fisher matrix calculation on this, and I can compute the error on A. And you get this. This is a very simple expression. When I compare this expression versus this is what I obtain. You can see that they agree very well. Now the mean value is 1 by construction, and this is the error. So when you compute the error from the Fisher with the error that I'm getting from the network, you can see that I'm only doing like a 2% worse. I can do even better than this. I will need to train this more, maybe play with architecture, but what you can see is that the network has learned to do the very best possible that you can do. It has basically learned to do all these things, like computing the power spectrum, do the maximum likelihood, or maybe it's doing something else. But it has learned to extract the maximum information from the field. So this was the first thing.
Akko, can I ask a quick question?
Please.
Don't you have to train it with a range of A values? Can't the weights just remember that A equals 1? Exactly.
So in this case, unfortunately, I don't have the slide here, but I train on values of A from 0.7 to 1.3.
Okay. Because it said input 100,000 maps with A equals 1.
Absolutely. Otherwise, I think the distribution will be collapsed. No, it will always predict.
Yeah, exactly.
one.
Yeah, the neural network, you always have to train over a range of.
Exactly, exactly.
Okay.
But that's a very good comment. I will be going back to this because also the range where you train your network can have an impact because it's a prior, basically. So, but I will be back to this. Okay, now what I want to show you is that neural nets can learn to marginalize over baryonic effects by themselves. So how I'm gonna do it?
Wait, Paco.
Please.
Like, so your first bullet point, I mean, like, no, yeah, this slide. Like, so this first bullet point, I mean, like, so, like, how have you shown that? I don't understand.
So basically, what I'm saying is that this is my model.
Yeah, so for a Gaussian case, sure, but to say that I can extract all information, you have to show it for something harder than a Gaussian.
Absolutely, absolutely. This is, yeah, you're completely right. I should be only claiming this for Gaussian density fields.
Right.
And I'm very optimistic that I can extrapolate, but you are completely right. Yeah, yeah.
Well, the one thing that we've learned about neural networks is that we shouldn't extrapolate with them, right?
Yes, I mean, the thing is that I cannot prove this with a non-Gaussian density field because I don't even know what is the floor. I don't even know what is the maximum information that is there.
Well, we do, right? I mean, okay, like, so for cosmology, we know that we're starting from Gaussian initial conditions and that there's some nonlinear transformation of those initial conditions. And so we know that the optimal way to get the information is to reconstruct the final density field to get the initial density field and just measure its power spectrum, right? That's the best we could do.
So are you saying that all the information is in the initial conditions?
For cosmology, yeah.
I mean, only the initial power spectrum, right? Like for A, all the information is in the initial conditions for A.
Okay, I think we can be talking about hours for this. I've been having this talk with a lot of people, and I thought exactly the same thing as you said, Neil, and people convinced me that this is not true. The transformation that you also have from the initial conditions to the final condition, that transformation itself also contains information. For instance, thinking an n-body simulation, I can start with the same initial conditions, but depending on my cosmology, I can end up with different things. So the initial condition does not really contain all the information. And we have also proved this, for instance, in Elena's paper. You can say all the information for neutrinos will be in the linear power spectrum for neutrinos. That's all I have in the initial conditions. What Elena showed in her paper is that she can do better when you take the redshift 0 power spectrum. And this is because the transfer function of neutrinos itself contains cosmological information.
Oh, sure, right. So if I could measure like the linear power spectrum as a function of redshift, then you agree that that would contain all information.
Yes. Yes.
Well, I mean, I don't see why that should be true. I mean, the information about initial conditions is in the initial conditions. I mean, that's kind of a tautology. But anything about the dynamics, there could be more information that comes from nonlinear dynamics and evolution in general. So I think those are kind of different statements. But I think the fact that just getting the initial condition reconstruction, if you could do it perfectly, that should be all you need, right? If you only thing you care about is initial condition, like the initial amplitude. And that, I don't think there is any debate about that.
Right, but for instance, the example that they put me, think about like dark energy or early dark energy. If I go to the initial conditions, I don't know anything about dark energy. There is basically nothing there. So how can I?
No, that's fair enough. I mean, that's not a statement about the initial condition. That's a statement about the dynamics. And then there is information in linear dynamics and non-linear dynamics and everything.
Exactly.
But, yeah.
So all I'm saying, Neil, is that I don't know how to quantify this information that is also in the dynamics, in the transformation. And we should talk later. I mean, I would love to do this because I can really compare the neural nets against that. If I really have a floor, I can compare this.
Yeah, but maybe like one sort of like, useful floor just would be just to, see how well you would do if you could measure the linear power spectrum at all redshifts.
Yeah. At all redshift, yeah.
Because there we know that it's just Gaussian, and therefore we know how much information there is because it's just the power spectrum then.
Yep, yep.
And that comparison, you know, already I think would be interesting.
Yep. Yeah, I mean, it would be nice to maybe talk offline because I think, Neil, yeah, I can be talking for hours about this. Yeah. So, yeah, so all this maybe a strong statement that I'm doing should be also made for the Gaussian field, but I really believe that this could apply to non-Gaussian density fields because, again, a neural net is just gonna look through all the possible things and it's gonna take the best one. Okay, let me talk about baryonic effects. How I implemented baryonic effects in this toy example. So now what I have is my power spectrum on large scales is a power law, the same thing as before. So an amplitude and the square root of k. But now on scales below this k pivot, so on scale, I'm basically changing my power spectrum. I'm basically assuming that the power spectrum is gonna completely change. It's gonna be a different power law. Let me illustrate this a little bit better. So these three images that you have here, these are Gaussian density fields. All these three different images have the same power spectrum on large scale. You can see here in the bottom panel. But on small scales, the power spectrum is different. And you can see that they have different amplitudes, and that's why the images look different. So my model is that on large scales, I have this A, this is my cosmological parameters, but on small scales, basically anything can happen. The power law can completely change. So what I will argue if I, as a physicist, is that the maximum information that I can get is gonna be until this K pivot. Anything beyond this, it will not have any cosmological information. And basically, if we train a neural net to do as best as possible, the neural net is basically should learn how to extract information down to this scale. And it also should learn by itself what this scale is, because I'm not telling anything. And then computing the value of A from this. So you can do the same exercise. You have these maps. Now you have maps where different cosmologies, so different values of A, but also different astrophysics, where you vary these C and D parameters. You just vary within a given range. And you train a neural net. You say, okay, given this map, this is the corresponding value of A. And you do this, you do this, you do this, and you train your network. So if you do this, what you obtain? So once the network is trained, now you input, let's say, 100,000 maps. In this case, again, I fix the value of A to be 1, and I put this K pivot to be 0.5. Baryonic effects will start kicking up at K larger than 0.5. For each map, I will get a value of A, and if I plot the distribution, I get this green line, you can see here. And again, because I now know where to cut, I should be cutting at 0.5, I can also do a Fisher matrix calculation. And the Fisher matrix calculation is shown in magenta. And you can see that the agreement is very good. And if you compare the errors, this is the mean value and the error, you can see that we're only doing like 1% worse, the neural net. So the neural net, without me telling anything, has learned to basically extract the maximum information possible and has learned to marginalize over baryonic effects. And again, this is for a Gaussian density field, but we believe this can be done for a non-Gaussian density field. And I will be talking later. This was the second case. And the last thing that I want to say about this is that let me explain. Consider this first case where you only have a cosmological model. There is no baryonic effects. It's just a power law. The power law, the error that I was getting was this, 1.1 10 to the minus 3. Then I show you that I put baryonic effects at K of 0.5. I trained the network. The network was giving me an error of 1.7, larger, and of course expected. You are basically removing all this information. The network has learned to completely ignore all these scales. What happens, because this is what I was doing initially. What I was doing initially is that I have a power law on large scales, and then I have another power law for very small scales. but I want the power spectrum to be continuous. I don't want to be discontinuous. So I repeat the whole exercise with this. And you know what? The error that I was getting when using this configuration, I was getting this. And it's like, wait. 1.5, I mean, the Fisher matrix, I already know that it's 1.7. Are you telling me that I'm doing better than the Fisher matrix when the power spectrum is continuous? So what is going on here? So it took me a while to understand this, but what is going on is that when the power spectrum is continuous, you have this relation, you know, I mean, basically the cosmology match the astrophysics. And what I believe is happening is that the neural network is using the information that is on these scales to basically constrain C and D very well. And of course, the smaller the scale that you go, the better that this constraint is going to be. And if I know C and I know D, I will also be able to say something about A. Or in other words, the network is learning that all these points basically are pointing towards this point. So I will be able to get the amplitude of this point very well. And this point depends on A also. So I believe that is what the network is doing. But basically the network is doing better than the Fisher. So basically if you completely remove all these scales, the network is doing better. And I believe it's just doing this. So this is to emphasize that in principle, if there is cosmological information that is embedded into the regime that is completely dominated by baryons, then neural networks might be able to extract that information.
Is everybody else seeing him frozen?
Yeah.
Yeah.
A long pause.
Yeah, I was thinking it was like a dramatic pause, but maybe it's too dramatic.
Yeah. I guess he's gone now, right?
The machine got him in the end.
Yeah, exactly.
It seems he lost the connection again. He's trying to connect. You are muted, Paco.
I apologize once again. Yeah, I know that I have to change my internet company just after this seminar. Okay, so I will probably just conclude, Elena, right? I just want to mention that basically in order to tackle all this approach that if you can simulate your data and you have different baryonic effects implemented, you can in principle get the maximum information there. Again, in extrapolating, as Neil said very well, but this is the idea. Then we have been developing this common simulation. So this is a suite of 4,000, more than 4,000 simulations. 2,000 are M-body, but we have 2,000 that are state-of-the-art magneto-hydrodynamical simulations. So these are run with the Illustris TNG and the SIMBA model. And yeah, we have more than 4,000 different cosmologies and different astrophysics. So this simulation has been really designed to try to see if we can really teach a neural network to extract all the cosmological information and at the same time marginalizing our baryonic effects. And in this case, we are really thinking in going to K of 30, K of 50, something like that. I will skip all this. Let me only maybe mention what is this this is the last slide. What is what we are trying to work on these days and what, yeah. So as I showed you in this Quixote simulation, what we have is an incredibly large volume, a volume larger than the volume of the entire observable universe. So hopefully this should be fine. We have recently also shown how you can do super resolution, also using deep learning. So you can take an M-body simulation and you can increase the resolution of this. So our goal will be to take this Quixote simulation and basically increase the resolution to resolve halos of 10 to the 9. And I think with this will be fine. Then we can use this camel simulation that is astrophysics. And basically what we're going to do is to train a neural net to learn how to paint, let's say, astrophysical things like galaxies or H1 or whatever thing that you can imagine from M-body to full hydro. And we are going to do this as a function of cosmology and as a function of astrophysics. So this will be the way for us to have millions of simulations with different cosmologies and with thousands of different astrophysics. Once we have this, we can just do this likelihood-free inference, training a neural net to give us the parameters. And again, I think that this is very, a little bit shocking, but I believe that this is the very best that you can do. I don't think you can do better than this if you just take a look at different statistics individually. So the conclusion is that the goal here is to get the tightest constraint of the cosmological parameters. I think this is the final goal. And that what we have been doing is this simulation or data-driven approach. Basically, try to simulate as best as you can what you observe. And because we don't fully understand astrophysics, then we need to marginalize over astrophysics. So we need to run simulation with different astrophysical models. But once you have this, in principle, a neural net should be able to find the optimal estimator that extract the maximum information and marginalize over astrophysical effects. So I will stop here and thank you and apologies once again for all the disconnection.
Thank you, Paco. Are there any questions?
I have a question. So what happens if the hydro sims, the baryonic physics in those don't capture the full range of, let's say, possible realities because they're missing some important physics?
That's an excellent question. So that's exactly what, in these simulations, we don't even have like one code. We have run simulation with 2 different codes. So I'm not an expert on this, but my understanding is that, for instance, this Arepo is solved the hydrodynamics in one way that is completely different to what this Gizmo code does. And the way that people in Arepo implement the supernova feedback or agent feedback, which is this Illustris TNG model, is also completely different to the way that these people in SIMBA, they implement this. So I didn't have time to show you, but even in some particular cases where we have trained, for instance, a very simple random forest regression using simulation only from SIMBA, and then we just see if this works for the illustrious TNG simulation that it has never seen and is coming for a completely different set of hydro implementation, this seems to be working right now. We are really able to get the value of the cosmological parameters.
I think I was thinking of a more even bigger question. If you had done this, if all this had happened in the early 2000s, there would have been no AGN feedback in anybody's simulations because they didn't really think about it.
Yeah.
Yet, of course, the simulators claimed that they predicted, accurately predicted all observables. It just wasn't true. So could the same scenario be true today? There's some important physics that nobody's simulations have, and maybe it's important. It's a highly hypothetical question, but
you are completely right. So we have been also thinking about this. So our approach in this case will be to do some kind of anomaly detection. So for instance, you produce your best simulation ever, and then you can really compare this with observations. So if you compare things like the stellar mass function or the power spectrum, maybe you will match all these things. But ideally, what you would like to do is to compare these two things at the field level. And there is this mathematical distance that is called the Wasserstein distance. That basically is a way to really compare fields among themselves. So if for some reason the fields doesn't match, it's going to show up something. It's going to show like there is some anomaly, probably in our simulations. And then, as you say, we should go there and try to understand what is missing, what is the physics that we are missing, and try to implement. But you are completely right. So if we are missing, I don't know, like X-rays, for some reason they are important, and we don't include in the simulation, then yeah, this will produce a bias in our results. Yeah.
Okay, thanks.
Thank you. Thank you.
Any other question?
Can I ask a question? So could you explain a little bit more how you can detect anomalies? Because I mean, if I have like a power spectrum, I say, okay, so there are these points that don't match my power spectrum, my theory. So, but here you have all these huge data sets with lots of simulations and then the data. So, and you don't really have a curve that you look at and say, here it fits and here it doesn't fit. So can you tell us what it is, that is a technology that tells us what fits and what doesn't fit?
Yeah, so unfortunately I didn't have time to talk about this, but I can mention this. So what we are thinking is in these autoencoders. I don't know if you are familiar with this. The idea is that you take one of these images, and this can be anything, right? It can be a 3D field with galaxies. What you do is to compress this data into a lower dimensional vector, like for instance, the power spectrum or anything. And then basically from this compressed statistics, you try to reconstruct the images. So for instance, if you do this, in this case, we obtain this, and you can see that the images, they look very well. Mm-hmm. But if you have data that is really anomalous, what is going to happen is that when you input one of these images, this network is not going to be able to reconstruct this image very well. So basically, when you compute the distance, the traditional distance between this image and this one, you will see that you get a very high value. And this is basically the way that you identify anomalies. This is not going to tell you where the anomaly is, but this is going to tell you that this image itself is anomalous. There is something here that it comes from a different pattern that your data.
Mm-hmm. So, I mean, what are the choices that you have to make to do this? Like, I mean, when I do usual data analysis, say I can look at power spectrum or mass function or say void mass function or things like that. So here, I guess you somehow you want your machine learning to decide what is the right vector compression, I guess. Yeah.
Exactly. So the autoencoder will automatically learn. So for instance, let me show you. So this is for temperature fields. And here, we are able to reconstruct the images beautifully well. So what we did was once we trained this in temperature maps, we input this thing, and this is the logo of this simulation. Mm-hmm. So as you can see, I mean, this thing doesn't really count. It's not a temperature map. Mm-hmm. So when you try to reconstruct, even though it looks very well, but for instance, if you look at the letters, you can see that this is not really reconstructing this very well. So basically, this automatically is telling you that this camel has nothing to do with the temperature map. This is an anomaly. So that's the way that this works. Yeah.
Okay, cool, thanks.
Thank you.
Any other question? I have one actually. So how are you thinking about combining the N-body with the hydro, like the Quixote with the camels?
Yeah, so
full scale, I mean, be able to look at all the scales?
yeah, so in camels, we have both N-body and full hydro with the same resolution. So you can always say that, you know, given the matter field, try to predict, for instance, the galaxy field.
Mm-hmm.
And again, there is an input that is the dark matter field, and there is an output that is the galaxy field. And they should be connected, right? I mean, so a neural net will find this relation. So the only thing, if I have this, the only thing that I need now is a matter density field from very large scales. And this is where the Quixote comes, because Quixote is giving me the large scales, and then I can just basically paint on top of Quixote once I learn the mapping with camels.
But you need to do it once you have also make the Quixote more high resolution, I guess, or not, or it doesn't matter.
I lost you for 1 second, Elena.
I was saying, do you also need to make the Quixote more high resolution in order to do this mapping, or it doesn't matter? Okay.
We need to make higher resolution, and that's why we need also this piece, the super resolution. But we have already done it, not to the 10 to the 9 solar masses, but yeah. Otherwise, I mean, think about running 1 gigaparsec box with full hydro is even impossible these days. I mean, I think you can even take like a supercomputer and you will never be able to do this. And here we're thinking in doing this for millions of simulations where you change cosmology and you change astrophysics. So I don't think there is other way if we don't do this.
Okay, so if there is no more questions, we can thank Paco virtually. And
thank you. I'm sorry again for the interaction. Yeah.